Welcome to the Model-Based STPA tutorial, where the idea is to combine system-theoretic development and safety approaches. My name is Alexander Albrecht and I'm currently working as a scientific associate at the German Aerospace Center. For those of you who are not yet familiar with the STPA or System-Theoretic Process Analysis, I will give a quick introduction. It is a rather new safety analysis approach that targets to identify not only component failures, but also issues that can arise from missing or inadequate system specifications, or also complex system interactions. Overall, the analysis premise is very interesting and has proven its applicability for nowadays complex systems. The profile that will be used in this tutorial originated from the idea to seamlessly integrate the STPA in developments of safety-critical systems, which incorporate approaches such as model-based systems engineering. Since the underlying language of model-based systems engineering is often the systems modeling language, a profile was created to allow the execution of the STPA within a MBSE environment, but we will hear more on it later. To motivate the topic, we will glance at the current trends in the aviation domain. What we can observe are emerging segments such as urban air mobility, as well as the need for more sustainable aviation. For these segments, novel vehicle concepts will be required that face various technological but also developmental challenges. Some examples are the demand for more automation, the increasing software intensity, and the reduced development time due to strongly contested urban air mobility segments. To deal with these challenges, adaptive approaches are necessary that help to develop these new vehicles in a safe and efficient manner. As a result of these trends, the idea of my PhD topic is to provide some answers to the following research questions. How can we use model-based developments to tackle the recent challenges? How would a safety-guided architecture design process look like? And how do we achieve a fast-paced but still certifiable design process? To set proper expectations for the tutorial, I will briefly elaborate the tutorial focus. It is targeted to explain a proof of concept implementation of a SysML profile for the execution of the STPA in an MBSE environment. It will not be a perfect depiction of the STPA execution, and a resource for getting knowledge on this topic will be the STPA handbook. It is also targeted to demonstrate the profile application with the Cameo Systems Modeler version 19.3, but we will not have a full in-depth explanation of every modeling step, since some basic modeling knowledge will be assumed. Herefore, a resource would be the Magic Grid Book of Knowledge. Furthermore, the demonstration of advanced implementation concepts will be targeted that can support the analysis execution. But the implementations might contain errors and should be viewed as a proof of concept rather than a qualified implementation. In terms of the agenda, we will start with a brief overview of background information and the resulting concept that integrates the introduced methods. Afterwards, the STPA profile itself will be explained shortly before diving into practical application. In the practical part of the tutorial, we are looking at the basic use case application first, and then also take a look at the demonstration of some more advanced concepts that try to address the development challenges that we currently face. Within the practical demonstration, we will switch between the usage of slides to outline our approach and the demonstration in the Cameo Systems Modeler SysML tool. Finally, future work will be outlined and a short discussion and conclusion provided. Since model-based systems engineering, or MBSE, is the central development approach that is assumed as the baseline for our process, it will be explained first. The two letters SE in the acronym represent the underlying concept of systems engineering. Systems engineering can be described as a transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems using system principles and concepts in scientific, technological, and management methods. This means that systems engineering provides a systematic development approach that is applicable throughout the whole system life cycle. One of the main problems with applying traditional SE approaches was that all parties involved in the development of the complex system were working with their own documentation. Between the documents, multiple implicit relationships were present that are not really transparent. For instance, if a discipline changes something, this should be broadcasted to everyone that is impacted by the change, which was not possible with the document-centric approach. Accordingly, model-based systems engineering was introduced that uses a central system model to address these consistency issues. It can be described as the formalized application of modeling to support systems requirements design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout the development and later lifecycle phases. Overall, MBSE builds on the systematic nature of systems engineering and formalizes and centralizes it to achieve a better traceability as well as possibilities for automation through its more formal characteristics. After elaborating the underlying idea of MBSE, we can take a look at some of its properties and potential relations to other approaches and processes. First, one of the key properties of MBSE models are their semi-formal nature. If correctly applied, this characteristic allows the advantageous combination with formal methods. Second, traceability of the model helps to establish change impact considerations and therefore supports the ideas of iterative and agile development approaches. At the same time, with clearly defined diagrams, the idea is to establish a clear understanding and communication between multiple stakeholders, again supporting agile principles. This also relates to the third property, because the model is simultaneously used to document the system as well as the design decisions, both being a critical component for certification. Finally, it is possible to integrate further activities such as the safety analysis into the process, as we will see later in this tutorial. In addition, I want to mention that between the adjacent methods, various relations exist. These will be highlighted in appropriate places throughout the tutorial. As we observed with the properties of MBSE and the related methods, the relation to safety analyses can be established. Due to the changing properties of nowadays software-intensive systems, we will also require adjusted safety considerations. In my opinion, the STPA is a good starting point due to its alternative and systematic analysis approach. Similar to MBSE, it is based on a system-theoretic background and therefore immediately indicates a good fit. To identify accident causes, the system safety is analyzed out of a control perspective. Hence, the system is modeled in form of a control structure as visible on the right side. Controllers provide control actions to a control process and receive feedback on the current status. To identify the control actions that have to be executed, each controller has an underlying process model that helps to decide on the actions to execute. Such a control model is then used to identify potential hazardous scenarios that could lead to an accident. In this regard, the idea is not only to identify accident causes based on component failures, since recent accident causes are often based on inadequate specification and interaction issues. Therefore, the analysis not only tries to identify unsafe scenarios that are triggered by a failure, but also unsafe scenarios with different and more recent accident causes. Interestingly, the analysis can also be applied to multiple emerging properties, such as safety and security. However, in this tutorial, we will focus on safety examples. Before we can start to apply the profile, we need to take a look at how the analysis is executed. Accordingly, the typical 4 steps are displayed on the right. The analysis starts with defining the purpose of the analysis, where we define the system, its boundary, and also the environment. In addition, we identify losses and hazards that we want to consider in the analysis and use this information for the following steps. The second step is the modeling of the control structure, where we model the interactions between the controllers and also between the outside environment. This model of the control structure is used in the third step to identify unsafe control actions. These unsafe control actions are actions that could induce a hazard and should be prevented. If such an unsafe control action is identified, we go to the fourth step, which is identification of loss scenarios. Loss scenarios are the underlying factors that could lead to the execution of an unsafe control action and subsequently a hazard and a resulting loss. When loss scenarios are identified, the next step would be to derive appropriate mitigations to prevent them from occurring during system operation. As a final note, it also has to be mentioned that the STPA structure includes some formal aspects which can be leveraged to automate parts of the analysis, as we will see later. The more formal structure also leads us to our last topic to introduce, the formal methods. Formal methods are mathematic-based techniques used to specify, design, and verify hardware or software-based systems. Advantages through formality are that we can achieve a more precise specification and also enable machine readability and subsequently automation. Since we plan to use an MBSE model as a central tool, we also need to consider the corresponding formality. And in fact, formality can be rather easily established in a model-based context by using clearly defined relationships between model elements. For the future, I'm looking forward to the SysML version 2 due to multiple reasons. One of them is the even increasing formality and the standardized API, which will be parts to consider for the STPA profile in the future. If we recollect the background information, we already identified related methods that can be combined to a process baseline. As the foundation, MBSE provides a systematic development framework and a semi-formal baseline for the development of future systems. When integrating appropriate safety analyses such as STPA, we would be able to allow for a simultaneous consideration of safety during the development and could even establish a safety-guided design process. Finally, since we want to be as effective as possible, we could leverage the semi-formal nature of both approaches to enhance the application. In my opinion, error-prone tasks should be automated, and therefore more time for creative tasks and the identification of complex accident scenarios should be provided. Before going into the STPA profile, I wanted to provide a disclaimer. The tutorial represents my own opinion and implementation, which might contain inconsistencies with the original ideas of the STPA. The current profile implementation does also not fully adhere to the STPA profile of the risk analysis and assessment modeling language. Overall, I would recommend to consult sources with the expert knowledge on the topics, such as Engineering a Safer World, the STPA Handbook, the MIT Partnership, and also guidances such as SIE and the RAML specification. Now it is time to take a look at the profile itself. Therefore, we're going to step back from the presentation mode and dive into the tool. In the tool, we can find the STPA profile and also an overview diagram that outlines what kind of packages are included. The most important part are the stereotypes that build the foundation to execute the STPA within an SysML environment and will be explained soon. In addition, we also find a library with instances of the stereotypes and, more importantly, some guiding tips and comments from the STPA handbook. For instance, we can find common mistakes when identifying hazards, losses, or also modeling the control structure. Finally, we also have some packages where additional functionality can be found, such as functionality to automate parts of the analysis. Other examples are metric extensions to track the analysis progress and validation rules to identify inconsistencies within the analysis. For each of the functions, a brief documentation is also provided in the tool. Let's take a look where the packages are actually located. And they can be easily found because they are directly at the first level of the STPA standalone profile. At the end, I also want to mention the profile diagram, which displays a holistic view on the profile itself and also already shows important parts like the stereotypes, usage examples, and also examples that can be helpful in identifying potential loss scenarios. Before going into the application of the profile, I try to order these stereotypes in a way where we see the relation to the STPA process. SysML stereotypes provide the ability to introduce new modeling concepts into the application in the tool. As visible, each stereotype serves a purpose on reflecting aspects that are either required to execute the STPA or help to refine the application. First, the purpose of the analysis is defined by using hazard and loss stereotypes. Afterwards, the control structure is modeled by using stereotypes for the control structure itself, but also the underlying controllers. Similarly, the interactions are addressed by the feedback and control action stereotypes, and their process models are documented with the usage of process variables that can be attached to the corresponding controller stereotypes. The identification of unsafe control actions is always executed with the context in mind, that is defined with an according stereotype. Next, the analysis block stereotype allows the engineer to identify unsafe control actions in a table-based format by following typical STPA guide words. When unsafe control actions are identified and the resulting hazards linked in the analysis block, the information can be directly used to create subsequent unsafe control action elements. These elements can be represented again in a table-based format and help to find potential scenarios of their occurrence, called loss scenarios. Each loss scenario is again documented in an own element and linked in the UCA elements. Finally, we also have some supporting stereotypes that will be mentioned in the advanced application later. To demonstrate the STPA execution with the profile, we follow the displayed framework. First, we're going to introduce a basic system model, which will be used to test our approach. Then we are going to follow the typical 4 steps while using the STPA profile stereotypes. So defining the purpose of the analysis, modeling the control structure, identifying unsafe control actions, and then identifying loss scenarios and introducing mitigations. For the basic use case application, we are not going to go into detail for the supporting activities, but they will be explained afterwards. To set up the STPA analysis folder structure in the model with just a few clicks, it is possible to copy it out of the profile library that includes multiple usage examples. This copy and paste trick is handy in multiple cases and can help in setting up tables or also other STPA elements. Since our goal in this tutorial is to show how to systematically evaluate the safety of a system, we first need to decide on the application example. Hence, selecting and modeling a system to evaluate is one of the first parts that we have to do. One of the steps into the direction of urban air mobility is the increased usage of lightweight piloted aircraft. So this is also the system that we selected, and let's see how the system is represented in the tool. Considering our framework for the tool example, we can go directly into the logical architecture diagram of the system structure. Here we can see that we identified the aircraft as the main system that we want to analyze, and we also decided to use only 4 parts for simplicity, and 4 parts are the pilot that is actually inside of the aircraft, the sensor unit that provides information. We have an aircraft control system that is able to handle the control of the aircraft when given the right commands. And we also have a collision avoidance system that assists the pilot in an urban airspace flight scenario, which is characterized by increased traffic. If we go back to the framework, we can also see the internal logical architecture is represented. So we can take a look at how these systems are actually interacting with each other. And here we see that the sensor unit is given information through an antenna system, then it calculates an aircraft state that goes into the collision avoidance system, which provides advisories to the pilot and is also able to receive changes in terms of its own mode. The pilot is also able to handle the aircraft control system, and in a tricky situation can also command an evasive maneuver to the aircraft control system. Otherwise, we have the ability for the pilot to also communicate with the traffic controller by providing the aircraft movement, and he's able to get instructions back which help him to decide on the control of the aircraft. We already have not only the components here, but also their interactions represented, which is done by using signals in the modeling tool. So let's take a look at the signals that we used. And here we just see what we've already seen on the diagram beforehand. We have the different signals that are placed on the connections between the parts. After selecting a lightweight aircraft for future urban air mobility as the target system and modeling a simplified overview of it in the tool, our next step will be based on the STPA execution. Accordingly, we need to define the purpose of the analysis by first defining losses and hazards that we want to consider. The classical approach in the STPA is to collect all losses that shall be prevented and then to identify hazardous system states that could, in worst case situations, lead to the losses. In the tool, we start by extending the profile with potential hazards related to the aircraft. As we can see, we already provided two examples. The aircraft state is wrongly interpreted, and the aircraft follows a dangerous flight path. Simultaneously, we can see the first application of an STPA stereotype that was introduced with the profile. Namely, the hazard STPA stereotype is attached. To show how hazards can be modeled, we will add one more to consider that is related to the collision avoidance functionality of the aircraft. Our additional hazard is the aircraft violates minimum separation standards. Similar to the hazards, we also need to define the losses that we want to consider during the analysis. So let's take a look at the losses diagram, where we already provided some examples, such as increased workload, reduced customer satisfaction, property damage, and people injured. The worst loss could be something like the loss of aircraft. So let's extend the diagram and also consider this worst case scenario for our system. After modeling losses that we want to prevent and hazards that define a system state that could cause them, a tracing should be established to define their relationship. In our example, the hazard aircraft violates minimum separation standards can be traced to multiple losses, such as loss of aircraft and people injured, as visible on the slide. The next target would be the modeling of the control structure. Before we do this, we will need to finish the definition of the purpose of the analysis by also defining the system boundary and the outside environment that we want to consider. After this is done, we can go into the modeling of the internal control structure and the corresponding interactions. We can see the modeling of the control structure here, and first dive into the control structure block definition diagram, where we can see the parts of the aircraft that we've already showed in the logical architecture view and that we want to reuse in the control structure and STPA considerations. In addition, we also see one example for an environment actor, which is in this case the traffic controller. As an overarching block, we provided a control structure block where now corresponding stereotypes will also be attached. So for the control structure, we need to attach the control structure stereotype. And for the other parts that we want to consider as controllers in our STPA analysis, we need to provide the controller stereotype. After defining the controllers that we want to consider during the analysis, we can go into the interactions between them in the control structure. And therefore we used an internal block diagram of the control structure that we can see right here. We reused the internal logical connections of the aircraft model, so the flow through the sensor unit, collision avoidance system, the pilot, and we can now also see the additional extension with the environment actor, the traffic controller. In addition to that, we also divided the interactions into feedback and control actions. And we tried to adhere to the hierarchical idea of the STPA, where feedback is provided upwards and control actions are provided downwards. As an addition to the interactions, we can also see the properties which represent the process models in our case. So we just added a few examples, but in my opinion, the process model is very important to also identify potential failure causes afterwards. So we added two properties to the pilot, the model of the collision avoidance usage, and the second one is the model of the control system usage. Adding these process variables actually works like this. We go back to the diagram where we defined controllers themselves, and we can actually enable to see the properties. So now the properties are also displayed and can be viewed in the containment tree of the model. So here we can actually also look at the stereotypes that are attached, and we see the process variable stereotype is attached to this property. If we wanted to add another one, we would just need to create a property and we would name it accordingly, like the model of collision avoidance usage. Importantly, we also already stated that the interactions are actually either control actions or feedback, but currently they were only specified as signals. So this is also something that we need to do. What we do is we created a diagram where we can see the signals that we want to use, and we can classify them in the appropriate categories. So these three are control actions. So let's add the control action stereotype. And the other ones are feedback interactions. Now we are actually ready for the next step of the analysis. According to the STPA execution, the next step is to identify unsafe control actions, since it is best to also directly consider them in a context so that we are able to identify loss scenarios. A context stereotype was added to the STPA profile that is used in the following way. For each interaction to analyze, we are able to define as many top contexts as we want. Each top context is represented with an enumeration where values can be added that will be present in each context. With the top context, we basically specify a baseline scenario that we can vary into more specific variations by adding additional context using dependencies. In each context variation, values can be added. In the end, scenarios will be created that combine the states of the context in a cross-product manner, while at the same time always using the top context values. For instance, for the interaction, the combinations in the table below will be created. First, we will have a scenario where we have the top context top value 1 and also the context 1 subvalue 1, context 2 subvalue 2. This is the first scenario that is created, and the second scenario that will be created by the specification is the top context 1 top value 1 again, but this time the context 1 subvalue 1, context 2 subvalue 3. So actually the cross product of these combinations. To make it more clear, we will show it in the tool. for our own example system. Hence, we go into the context STPA folder and diagram, and here we can see the definitions that were already present in the slide. So if we want to actually model something like this for our system, where we want to consider the evasive maneuver command that is provided from the pilot to the aircraft control system in a context where an intruder is present and in a context where no intruder is present, this is actually modeled right here, and we have no additional top context values attached. So let's model this example ourselves. We can use the drop-down menus that are provided in the block definition diagram, and we can say we want to analyze the evasive maneuver in one top context, which is provided under the situation stereotype. So we can say top context 2. Then we also need this relationship, and it was defined to be a dependency. So we use the common menu and attach a dependency. And we also want to define the more concrete values that will be used in combination. And herefore we use a context stereotype, name this concrete context. And then we can also add enumeration literals where we define the values. And in this manner, we could also define the same situation to analyze as we did on the left side. To finalize, we also would need to attach a dependency here. After defining the context in which we want to analyze the evasive maneuver command, we can actually use the first automated functionality that was provided in the profile. To do that, we go to expression evaluation and we select the structured expression because we want to execute an operation from the model, because these functionalities are implemented in form of an operation in our profile. And we want to create analysis blocks for the STPA, and therefore we need to define first the item flow folder. So this is a folder where the interactions are specified between the system elements, and these are defined in terms of item flows. So we need to define in which package this is, and we can just use the package because we see here the item flows are actually defined. And in the next step, we also want to say where to put the analysis elements when they are created. So we go under the test package, go to the appropriate folder under the identify unsafe control actions folder, and we say we want to put them into the analysis blocks STPA package because we are currently creating instances of the analysis blocks that will be used to identify unsafe control actions. We say OK and execute the functionality. After executing the functionality, we can take a look in the corresponding folder, the analysis block STPA folder, and we created a bunch of examples to analyze. Because we already prepared this beforehand, we can just delete them again and take a look at the ones that were prepared beforehand. So we can see the two are created for the interaction control action, and we also have the ones that can be used to analyze the evasive maneuver. And here we leverage the analysis block stereotype and the different properties of the analysis stereotype. And as we can see, a lot of parts are already provided automatically. So the context that we want to analyze the control action in, and also the source and the receiver are automatically provided. The next step would then be to identify, using the guide words, which hazards can actually occur in this context when this action is executed. When the intruder is present and an evasive maneuver would be executed, This sounds like a good idea. So if we consider the guide word not provided in this context, we might have a hazard. One example would be if there's no evasive maneuver executed, we might violate minimum separation standards. So we can actually attach the hazard to the table element, and now we defined one example how this evasive maneuver could go wrong if it is not executed when an intruder is present. Let's say this is all that we wanted to do here. So we can say we analyzed it, and we also provide our name to make it clear that you can trace the execution of the analysis back. The second scenario that we want to consider is the scenario where no intruder is present and the evasive maneuver is executed or commanded. This could actually also be not a good idea if this is done. So we go to the provided in this context column and add the hazard, which would be that the aircraft follows a dangerous flight path because of the evasive maneuver. We added the hazard, and we can actually say that we also assessed the second one and provide the name again to allow traceability. Finally, we also want to show that there are more guide words possible, so we could also analyze the situation in a more concrete context, like provided but applied too long, provided out of order, stop too soon, too early, and too late. These are examples that can even be extended and are selected to guide the engineer on potential problematic situations he has to analyze. The recent activities can be summarized as follows. We selected to analyze the evasive maneuver command that is executed from the pilot to the aircraft control system. Therefore, we specified a context in which we want to analyze this control action. Then we used the first automated functionality to create analysis blocks that guide us in the identification of unsafe control actions. And we initially documented these unsafe control actions by linking hazard elements in the guide word columns of the analysis block. This semi-formal approach also allows us to execute the next automated functionality, the creation of instances of the unsafe control action STPA stereotypes. Similar to the creation of analysis blocks, this is executed via an operation that is provided in the profile. So let's execute this using the structured expressions and using the operation from model. And this time we want to create UCA instances. And in this one, we have to provide 3 inputs. The analysis block folder, because they will be used as a baseline to create these unsafe control actions. Then the folder where the unsafe control actions shall be placed. The last one is the item flow folder, so again the test package. Then we can execute the functionality, and we created the recording elements. Since we prepared this step beforehand, we deleted the created ones again and only show the ones that are relevant to our example. In the analysis block, we specify 2 entries, which are represented by the 2 resulting unsafe control action elements that are created by the functionality. The semi-formal nature of the analysis block allows the subsequent creation of the corresponding UCA descriptions. As we can see, we identified the UCA that the pilot does not apply the evasive maneuver to the aircraft control system when intruder status is in state intruder present. And we also identified that the second unsafe control action would be that the pilot applies the evasive maneuver to the aircraft control system when intruder state is in state no intruder present. What I personally recommend is to exchange the automatically provided name of the UCA with a more expressive one. For instance, we can name the first one No evasive maneuver when intruder present leads to separation violation. The second one will be named evasive maneuver when no intruder present leads to dangerous flight path. Between the first and second UCA example, we can observe the entries that are automatically provided and the ones that we have to extend. Namely, everything up to the loss is entered automatically. This is done by either using the information from the previous analysis block or using the information from the control structure model. The first entries are derived from the analysis block, and the next ones are derived from the control structure model. These additional variables are provided to guide the engineer in identifying loss scenarios later, but this will be explained more in the next step. To understand where these variables are coming from, we need to take a look at the source of the unsafe control action, which is the pilot. If we step back into the control structure model, we can actually observe where all of these entries are coming from. So we have the incoming command variable, the instruction that is going into the pilot. We have the feedback variable, which is the advisory, and we also have the two process variables. And all of this information is used and automatically inserted in the UCA elements. In addition to the automatic creation of unsafe control action elements, we can also create requirements that remind us of the situation that we want to prevent. These requirements are also easily created with the cert profile functionality. So let's use the structured expressions again. Go to the operations and create requirements. For the creation of requirements, we have to specify the analysis blocks folder. As well as the requirements folder where they shall be placed. And then we just need to execute the functionality. As always, we prepared this beforehand, so we just need to go back into the requirements diagram, and we can see the two requirements that are created automatically. So the first one is the pilot shall always be able to apply the evasive maneuver to the aircraft control system when intruder state is in state intruder present. And we get the context reference, the receiver and action reference, and also the hazard reference automatically. As we can see with the requirements that are created, they should not be taken as 100% truth, but are just a reminder of the situations that we have to consider in the system design. With the prior creation of unsafe control action elements, we already laid the foundation to identify loss scenarios. Hence, we can consult the control structure model as well as the automatically inserted elements of the UCA table for identification purposes. If we have identified a loss scenario, we need to document and link it to the corresponding UCA. For this step, we make use of the loss scenario stereotype that provides properties to clearly document the underlying causality. The goal is to identify all loss scenarios that could lead to the execution of the UCAs and to derive appropriate mitigations so that they will not occur during system operation. For the first UCA, we have to identify why the pilot might not execute the appropriate evasive maneuver. To do this, we can consult the prepared information in the UCA element and also consider the control structure diagram itself. Since the source of the evasive maneuver is the pilot that does not execute it when it is required, we can take a look and identify loss scenarios that could be the underlying causality. So if we look at the interactions, we can see the pilot is on the one hand getting an advisory from the collision avoidance system, while also getting an instruction from the traffic controller. Both are interactions that influence the maneuver decision of the pilot. On the one hand, the traffic controller might provide an instruction, while at the same time the collision avoidance system can provide an additional advisory that could even be in conflict with the traffic controller's instruction. The resulting loss scenario would be that the pilot is not sure what to follow and therefore misses to execute the appropriate evasive maneuver, leading to the loss. For this loss scenario, even a third variable could be considered as a factor, the model of collision avoidance usage. If the pilot would clearly know the priority of instructions, this loss scenario could be prevented. For pilots in commercial vehicle, this priority was already clearly defined after a mid-air collision accident in Überlingen in 2002. But since we consider a use case for lightweight urban air mobility vehicles, we have to remind ourselves to also instruct the upcoming pilots of these emerging segments. Let's see how we documented the loss scenario by using the loss scenario elements of the STPA profile. For this, we step back and go into the loss scenario diagram, where we see the loss scenario no evasive maneuver due to uncertain instruction priority. We provided 3 causal factor sources: the pilot, the traffic controller, and the collision avoidance system, and the 3 causal factors: instruction, advisory, and the model of collision avoidance usage. In the end, we classified it as a process model causal factor issue and described it in the following way. Simultaneous instructions from the collision avoidance system and the traffic controller lead to a pilot confusion and a missing evasive maneuver. The corresponding mitigation is a requirement that was derived that states that the instruction priority between the collision avoidance system and the traffic controller shall be clearly defined. And this can be done through appropriate training, for instance. And the requirement was also linked in this mitigation column. To create such loss scenarios, we would just need to add a new element in this table, and then we can create another loss scenario. In the end, we also want to link the loss scenarios to the UCA elements. So we go to the corresponding UCA element and attach the loss scenario that we've described beforehand, which is no evasive maneuver due to uncertain instruction priority. After providing the loss scenario and the loss that can occur, and when we are also certain that we assessed all potential loss scenarios, we can also set this unsafe control action as assessed and provide our name to make sure that we have the traceability to the analyst again. As a final note, I also want to mention that the assessed and analyst properties are also present in the loss scenario elements. So we can say when we are finished with the loss scenario description and also providing the mitigation, and then we even have a field to state that the loss scenario and the corresponding mitigation was approved. And this could be something that is interesting for a certification agency that looks over the mitigations that were introduced and then can improve the loss scenario mitigations by using this approved property. The derivation of loss scenarios and mitigations also concludes the analysis. So let's recollect what we have done so far. We have used a system example, modeled it in terms of a logical architecture, where already some signals were provided. This was used as a baseline to then execute the STPA in the following way. We defined the purpose of the analysis by modeling hazards and losses. Then we modeled the control structure in more detail by reusing some of the logical architecture elements, but also extending it with a system context and making it more specific by providing the appropriate stereotypes for interactions, such as control action and feedback. Then we defined in which context we want to analyze the evasive maneuver, created the analysis blocks to identify unsafe control actions. We documented them as requirements and also unsafe control action elements. And then we used the information in combination with the control structure model to identify loss scenarios and derive corresponding mitigations to round out the STPA execution. After the basic use case application, some advanced concepts and functionalities will be elaborated that are also prototypically implemented in the tool. For reference, each of the following functionalities is also described in a corresponding publication. In my opinion, the following assistance functionalities are highly important for an integrated safety-guided design. They are currently implemented in the SysML profile and mainly for the Cameo Systems Modeler tool, but could also be incorporated in other tools with the same scripting and highlighting abilities. The concepts are not specific to SysML, which is also the reason why I now refer to the profile and related concepts as Model-Based STPA instead of SysML STPA. The first functionalities that I want to discuss were published in the Dusk 2021 paper. Here, the main concept was to automate error-prone tasks to support the engineer during the STPA execution. Included were aspects such as the creation of table elements, automated verification and validation activities, and progress tracking through metrics. In the basic use case application, we have already used some of the advanced concepts, such as the functionality to create analysis elements. So let's recollect. We created these analysis elements by using the defined context values and also the specifications in the control structure. Let's take a look at how the functionality is located in the profile. We can find the implemented functionality create analysis block instances here. And since we already showed how it can be executed, this will not be done again in the advanced use case application. The second functionality is also related to the analysis blocks as one of the examples, which is the verification and validation of entries. We could have the example that we analyze one situation and see that no matter if the action is provided in the context or not provided, we might have a hazard. So in this case, we would enter another hazard here. But if we consider this situation, this is something to prevent in the system. If we have a situation where no matter what we do, we still get a hazard, this is something we need to look into in more detail. At the same time, this could also be an entry that is just wrong, so this would also need to be highlighted to prevent the follow-up analysis of an unnecessary element. Here we have the validation activity that shows us that there's an issue with the current element, and we can resolve this issue by looking at it in more detail. If we want to see where it is implemented, we can take a look at the validation rules, and one of them is the one that highlights the situation. At the same time, we have another functionality that if we say we have one of the analysis blocks assessed, but we do not enter an analyst, this is also highlighted because we lose the traceability. A warning should be provided to don't forget to enter the analyst entry. The third functionality is related to the tracking of the analysis progress. And therefore, we provided the tracking implementation through metrics that can be used in the Cameo Systems Modeler tool. We have the analysis block entries tracked over time. And this can be very important for larger projects where we need to see how many elements we have to assess and the percentage-based process over time. If we want to add another one, we would just need to add a new metric, provide the scope, the analysis block folder, and let's calculate it. And we can see this time we have few more elements assessed as the last time we executed the functionality. The same can actually be done for the unsafe control action elements to also track the progress. In the previous examples, we discussed and displayed assistance functionality for error-prone tasks. Now we will take a look at the process and implementation extensions that were added to facilitate proactive application of safety within agile model-based developments. The idea is to use an advantageous integration of MBSE and STPA activities to improve the efficiency. For instance, between STPA and MBSE, we can identify some overlapping tasks. Exemplarily, the STPA requires a clear definition of a system context, which is typically also one of the steps in an MBSE framework. If we leverage the definition for both tasks, we are not doing the same task twice, so improve our efficiency. Simultaneously, such an integration of safety and design activities also allows us to directly incorporate the outcome of the safety analysis into the design. This could also be envisioned in an agile and iterative fashion. To support such an agile and iterative safety-guided design process, we will also need traceability of design changes towards safety artifacts. Fortunately, this can be supported by the following implementations. Essentially, the automated functionality always knows the required elements due to its specification, and simultaneously, the current elements can also be easily extracted from the tool. This allows us to always calculate sets such as the new and changed elements or outdated elements. Some of this functionality is prototypically implemented in the profile and will be demonstrated now for better understanding. We start to demonstrate this functionality with the consideration of the analysis blocks, because they actually represent a hazard table which could be one of the safety artifacts that we want to trace if changes occur. The analysis blocks are also created automatically. One of the reasons why they are created is because we specify a context in which the control action shall be analyzed. What happens now if we want to extend the context? We will also have to create new or adapted analysis block elements. To demonstrate this process, we will go back and into the context diagram. And in the context diagram, we had the context defined that we want to analyze it in a situation where an intruder is present and no intruder is present. Now we could also say that we want to extend this context and also want to consider that we are close to terrain. Subsequently, we will also need an adapted context that also considers this terrain relation. Through the implemented validation functionality, we will get notified automatically that we have an error, and in the error it is stated that there are missing analysis blocks because we extended the context and we now used the functionality to trace this back to the analysis blocks and identify that we need new ones that have to be created. To create them, we not only can use the functionality to create all of the analysis blocks again, but we can use specific functionality that is used to refresh the analysis blocks. So let's use the refresh analysis block instances STPA function and provide the item flow and analysis element package. After executing the functionality, we can take a look at the updated elements. And what we will see in the updated elements is that we have an extended context, because now we have the elements that we have the close to terrain context in addition to no intruder present and intruder present. So we updated the analysis blocks according to our new specification, but we only created the blocks that were necessary to update. The same concept can also be used for the unsafe control action elements, because they are also automatically created. And they are created considering incoming command, feedback, and process variables. So let's say we extend the process variables, and therefore we would also need to consider them in the analysis of the unsafe control actions that we already analyzed. So we go to the pilot and we extend the pilot by one additional parameter. Again, we can see an error pops up in the active validation, and we are notified that we need to update the UCA blocks, because all of the UCA blocks that are related to the pilot as a source will need the update. But before we do this, we want to also show the same concept considering the interactions. Let's say we want to add another interaction, for instance, a feedback that the collision avoidance system provides its own status to the pilot. What we would do is we would create a signal, collision avoidance status, and we would characterize it as a feedback variable. Then we would drag this feedback onto the connection and say it is flowing from the collision avoidance system to the pilot. After realizing it, we will also get a notification because we not only need to consider the advisory, but also the collision avoidance status as an interaction when identifying the unsafe control actions and corresponding loss scenarios using the unsafe control action elements. So the active validation rule states there are missing UCA blocks that need to be created. The third way of how we can trigger the need for a new unsafe control action element block is if we would extend the analysis in the analysis blocks. So we beforehand created the two updated elements, and maybe this changes also the analysis, and we now need to provide the hazards again and analyze it further. And now we also get two active validation results, because on the one hand we need to update our unsafe control action elements, but at the same time we also need to update the requirements that document the unsafe control actions that are inserted in the analysis blocks. In summary, we have used the safety traceability concept and the set relationships to implement functionality in the tool that notifies us when we change something in the design or in the context that would affect the UCA elements or the analysis blocks. Then we can get notified and use refresh functionality to update them accordingly. Such a functionality facilitates the execution of an agile safety-guided design and is the first step that was presented in the ISSE paper 2022. The last process improvement of this tutorial will be the discussion on supporting activities to automatically indicate and improve the safety analysis coverage. This concept was published in the DUSK 2022 paper and targets the issue that it is hard to claim sufficient safety analysis considerations for the current complex cyber-physical systems. Accordingly, supporting functionality is necessary that indicates missing considerations within the safety analysis, similar to a coverage assessment in the software domain. As a baseline for this functionality, the idea was to use the model-based links of the STPA analysis elements to automatically create a holistic summary of the STPA-related safety considerations. The resulting model-based analysis summary can then be used to enable different coverage indicating functionality, such as visual indication of identified failure causes in the control structure diagram, as visible on the right, and even statistical metrics indicating the depth of the analysis execution. To allow a basic understanding of it, I will try to briefly explain the underlying concept. If we take a look at the graphic on the left side of the slide, we can see the typical relations of the elements during a STPA analysis. Control actions are analyzed and unsafe counterparts called unsafe control actions are identified. Each unsafe control action can be triggered by one or more loss scenarios that again have their underlying causality. Causal factors can either be other interactions, process variables, or also the combination of both. As visible, each analyzed control action spawns one part of the formalized STPA summary. In the publication, this was described as each control action having its own failure graph, FG. Subsequently, in the image, we see the failure graph of control action 0 and control action 1. Interestingly, since the control action 1 is listed as a failure reason in a loss scenario of the control action 0, the failure graph of the control action 1 could be linked to the failure graph of the control action 0. To not complicate it further, we will now explain how we can leverage these failure graphs to analyze the coverage-related aspects and show it also in the tool. The first part that we can use is we can create these failure graphs automatically by just using a relation diagram in the tool. So we currently have it displayed for another interaction, but we can just drag the evasive maneuver into our consideration here. And what we see here are the relations between the control action evasive maneuver, the identified unsafe control action no evasive maneuver when intruder present leads to separation violation, and the underlying loss scenario that we identified, no evasive maneuver due to uncertain instruction priority. And since this instruction priority also considers the advisory, we could even link the failure graph of the advisory, but this will also be something that we see in the visualization. So let's consider the visualization next. We go into the control structure diagram, and to visualize the failure graph, we need a specific legend that is able to highlight the elements. And we prepared this beforehand, so we can just use and drag and drop the evasive maneuver failure graph legend into the diagram. As a result, we get highlighted a lot of features that are actually attached to the failure graph of the evasive maneuver command. Now we might think, how is the mode change related to the evasive maneuver command? And the reason could be that the mode change affects the collision avoidance system, which is then providing a wrong advisory or no advisory when required, and then we might not be able to execute the evasive maneuver when required. By looking at these relations, we also see the interconnections that we might have identified during the analysis. But we also potentially see the missing relations that we have not identified and analyzed during the STPA consideration. It is also possible to highlight different states. As visible here, everything is mitigated, and this is because we provided a requirement at every loss scenario that we've identified. Now we could also go into the loss scenario and change the state, either making it to an approved loss scenario or also taking away the mitigation, and this would reduce or change the state. Let's go back. After we changed the loss scenario to a state where this is approved, and since this was the only loss scenario that is related to the instruction and the advisory, we get a changed state, and this is also highlighted in the diagram. Finally, let's look at how this is actually implemented in the tool. For each of the properties, we specified elements by condition and used a functionality called evaluate approved and mitigated elements for smart legends. And we also provided the evasive maneuver as a considered action for this operation. In the current implementation, we automatically display all levels of the failure graph. So not only the first level that we might want to analyze, but this is something that could be changed in the implementation of the functionality that highlights the failure graph. The third concept in terms of coverage indications is the calculation of statistical metrics that indicate the depth of the analysis execution. So let's use functionality to calculate these metrics. And place them in the statistics folder. Now we go back and we can see the statistics that are now recreated for the evasive maneuver and all of the other control actions that we have analyzed beforehand. Now we identify that the UCA count is 2, the loss scenario count is 1 for the evasive maneuver, and since we just approved the loss scenario, we have an approval rate for 100% and also a mitigation rate of 100%. Using these indications, we can get an idea of how much time was spent on identifying unsafe control actions for each control action and also identifying loss scenarios. And we can also identify if we have mitigated and proved all of the loss scenarios. The second example that we can also create by using this functionality are the classifications in terms of the categories. For the evasive maneuver, the loss scenario was placed into the category classification of a process model. So we have one loss scenario that was classified as a process-related classification. Considering the other categories, we might have to analyze if an inadequate or missing evasive maneuver can be caused by an algorithm issue, a component issue, an environment issue, human issues, or other input or transfer problems. And if we have identified them, we would create these new loss scenarios, and they would also be represented in the statistics and can be used to argue the safety of the system later. Before going into the discussion and summary, I want to mention that I believe that there's a lot of improvement possibility for the coverage indication concepts that were currently discussed and demonstrated with the tool, as well as the implementations themselves in the STPA profile. After demonstrating the advanced application concepts, we reached the last section of the tutorial, which will provide a brief outlook on future work, as well as a discussion and conclusion. To understand the direction of future work, we will reuse the method relations that were highlighted in the beginning of the tutorial. Considering the creation of the profile and the first related concepts and papers published in 2021, we can say that we started to mainly target the relations between safety and formal methods. In 2022, we further advanced this work with the Dusk paper and also started to establish a relation between the formal methods and agile development branch with the change impact considerations in the ISSE paper. For 2023, the current plan is to also address the direction between the safety assessment and certification progress. As a general trend, it is visible that we start to branch down with the publications, and in future we'll try to incorporate all of the concepts into a holistic safety-guided design approach. Next, we're going to discuss some of the limitations in the current profile and application. One important fact to consider is that the analysis is only as good as the underlying model. Hence, we need a thoughtful modeling to identify as many potential issues as possible and thereby achieve a safe system design. Secondly, we can only use automation with caution, since there can be issues with the automation algorithms, the automation requires a formal structure, and using the automation could introduce too much reliance and reduce self-thinking, which is something to prevent. To manage these limitations, we can apply the following techniques. We can leverage the systematic nature of MBSE frameworks to identify the best possible representation of our system and explicitly analyze the model that is used for the STPA analysis for consistency. Simultaneously, we have to provide a clear training in the automation usage, correct automation algorithms, and can even use the information that is provided by the automation for an explicit completeness analysis. Another important discussion is if we can always just reuse the development model for the model-based STPA. Here, multiple potential issues have to be considered that are related to the control structure paradigm of the STPA. We need to keep the control-oriented view of the STPA in mind and model our control structure accordingly. We leverage process models in the STPA, which are not by default represented in a typical system model, but are an essential part for identifying loss scenarios. And we need to think about the abstraction level for the safety analysis to not overload our analysis. The learnings are that we need experience to model the control structure in the right way. Therefore, I once more want to recommend the materials of the STPA founders and corresponding sources that can be found in the PSASS materials page. Moreover, we need to additively describe the process models for the identification of loss scenarios. And we need to monitor the abstraction level for modeling and safety analysis activities. In conclusion, we started the tutorial by glancing at the current trends and resulting requirements, then identified multiple methods that could be helpful to address the development issues such as STPA and MBSE. Afterwards, we set up a concept of combining these methods into a holistic safety-guided design process. The concept was implemented in the STPA profile, and we demonstrated a basic use case application and also advanced concepts. Finally, we discussed the limitations and provided an outlook into future work by considering related publications. As a final note, images and other references are displayed in the slide, and are recommended to get further knowledge on the tutorial topics. Since there were also a bunch of related publications, we can find a list on the slide, and the corresponding links will also be attached for future reference. When using concepts from the STPA profile or the related methods, a reference to the related work would be appreciated. In case you have any question, comment, or suggestion, feel free to contact me under the given references. I'm looking forward to discussions on the presented topics and maybe even future collaborations.